All right, hello everyone. Now what we're gonna do is we're gonna start to implement some type of linear or not linear model, artificial neural network model for a data set that is collected for a river it's called Gila River in the United States. Let's first upload the data. It's called Gila River. Here it is, and I would like to see this data and see how it looks like. So first of all, I'm gonna import some sort of libraries that as we do every time, like we're gonna import Panda, NumPy, and scikit-learn model selection, do pre-processing based on standard uh, scalar. Here we go. These are several libraries that we upload. The new library here that we are importing is a multi-layer perceptron regressor. So this is basically the neural network model that we're gonna utilize in order to build a model for our system. So the second part is gonna be related to loading the data. So I'm gonna call data equal, and then I'm gonna import bb dot read CSV, and the dataset is called Gila River dot CSV. Here is the dataset Gila River. Okay, let's load the data, and then after that, what I'm gonna do is I'm gonna see the data dot. Uh, we need to see what we need to see the the information in the data set. So we're gonna load data.head to see the head of the data. Here we go. So this data is actually, as you can see, it has x of t minus 1. This is the first input. Actually, it's the delay of the y, which is the output. This is the flow. And then x of t minus 2. Possibly we can call it y of t minus 1. If I go back, let me go back to the data set here, because actually I made this changes. So I'm going to call this, because this is a regression model, so I'm going to call this y of t minus 1, and I'm going to call this y of t minus 2, and I'm going to call this y of t minus 3. Okay, so this is actually a delay. As you can see, what happened is this is the flow of the river, which I'm calling as y, and then I have one delay here, I have two delay here, I have three delays here. Okay, I'm going to save this file, and then I'm going to upload it one more time here. So I'm going to delete this file, and then I'm gonna upload it one more time after I made the correction modification. So this is a sort of data set that represents uh, a regression nature. Okay, so this is the output that we need to predict, and then we can also check the data dot shape, see how many samples do we have. So we have 2000 samples, and the size is 4. So y of t minus 1, y of t minus 2, y of t minus 3 are going to be um, the, uh, the delay or the inputs for my model, and the output will be y in this case. Okay, so to prepare the data for processing, what I'm going to do is I'm going to select x as input, and what I should do here, I should drop data dot drop. I'm gonna drop the last column, which is the output. I'm gonna drop column equal y. Okay, right. Of course, I can say I can column y, and then I call axes equal 1 to define as a column, and then I'm gonna write, I'm sorry, y. Let me write it small this time, and then this will be data, and the output will be the y itself. So this should give me the data set split as x has 3 column and y have 1 column. Now the next step is I need to split the data to training and testing, so I'm going to call x train, comma, x test, comma, and then y train, y test, and this shall equal to train test split. Okay, and then I'm gonna have the input x and the output is y, and then I will say test size equal, let's, as always we do it like 20%, and the random state equals 42. Okay, this should split the data to 80% for training and 20% for testing. Now the next step is I would like to standardize the data. So here we're going to standardize the data, so I'm going to call scalar. Here scalar, I'm going to call standard scalar. Okay, this is a standard scalar, and then I'm going to call the train data. Okay, equals scalar dot fit, right, and transform. Okay, and we're going to fit the x train, right. I'm just putting the scale data instead of x train, right. I can call it x train scaled if you like. That doesn't make a problem. I mean, we tried that before. And x test equals scalar dot transform. Okay, and this is going to be x test. Okay, so that should be the standardization of the data. Now the next step, I'm going to call the multi-layer perceptron regressor. I'm going to call it multi-layer perceptron equals, and this is multi-layer perceptron function that I'm going to utilize here. And then I'm going to say how many hidden layers do we have, hidden layer size. Let me define like 2 hidden layers, 64, 64. Of course you can play with this. I mean, you can try to define the number of layers as needed. If you want one hidden layer, if you want 2 hidden layers, if you want 3 hidden layers, and so on. And as you can see here in the demonstration here, or the help here, you can use certain activation function like ReLU, Solver, Adam, but most likely we use Adam and ReLU in the case of deep learning, batch size, learning rate. So this is like initial setup that we have, maximum iteration, but maximum iteration here is 200. I think we need to increase the size of maximum iteration. Okay, and we could also use some other attribute. I guess we can use the random state one more time. Could be, think, yeah, I mean, randomizing the like shuffling of the random values. But let's first use max iteration. Sometimes you get like an sort of uh, like alert that the network did not reach the maximum iteration. So might be good to have like large number of iteration, 1000, or maybe we can make it 3000. That's again possible. Okay, now if we run this, now the next step is we could start to do the training of the network. I would call multi-layer perceptron dot fit. Now this will do the training, and I'm gonna fit the x train, comma, y train. Okay, let's see. This process might take some time because we have 3000 iteration. If you have less number of iteration, maybe you can get it faster. The next step is actually we would like to do some sort of prediction, and as we did before, we were doing the prediction over the training and testing cases. So I'm going to define some variables called y train predict. equal, and then it's going to be multi-layer perceptron dot predict. As you can see, we always use fit and predict, and then I'm going to feed here the X train, yes, and then we do the same thing for Y test predict and X test. Okay, after we do that, we need to calculate the mean square error. So we're going to say mean square error over the training will equal to mean square error. Here is the function, and then we're going to feed what? We're going to feed the Y train and Y train predict, right? Okay, and then control A, control C, and then do the same thing. Y or this should be mean square error, not mean square R. Mean square error, mean square error over the test case. Okay, and this should be test, and this should be test, right? We run this. Okay, we have a problem here. Y test, Y train, this Y train, Y test predict, correct? Yes. Okay, now if I would like to print these values, so I can write a code here, which is, I can say print and F, then we can say training mean square error colon, and then we can add brackets to put the mean square error train, right? Then we can do the same thing here and put the testing case and mean square error test. Here we go. So this is a calculated error over training and testing. As you can see, the error is a little bit high. The mean square error, as we mentioned, it might not be the best criteria to provide the output or how it looks like. So first of all, I would like, before, I think it's a good idea to draw the actual and the estimated response or predicted response in both cases, the training and testing. But before that, I would like to draw the conversion curve for the multi-layer perceptron. I mean, like, to see how the error, the conversion of the error in this case is working, which is called the loss. So in order to do that, I will plot a figure. I say plot figure. Okay, and then I will define the fig size. The fig size, I will make it 5 and 4. You know, we tried different sizes before. And then I would say plot dot plot, and I would like to plot the multi-layer perceptron dot loss curve. Yes, this one. Okay, we need to draw this one, and the title would be the multi-layer perceptron convergence curve, and the lot dot x label. This is going to be like the number of iteration or epoch. Okay, and then after that, plot dot y label will be the loss function, and then we can have the grid. If you like to have the grid, it might look nicer, true. And then after that, we say plot dot show, and so we can see the conversion curve. Fig size, as always, we forget the equal. Here we go. So this is a conversion curve. As you see here, this is the iteration, and the number of iteration, and this is the loss, which is the error. So you see there is a conversion here for the network in this case. All right. Of course, if we make some changes to the number of neurons and iteration, I would like to try actually small iteration to show you if the type of error that we might get if you do not have enough number of iteration. And of course, the number of neurons here is a little bit high. I mean, we have 64. See that? So it says here convergence warning stochastic optimizer. That's what happens when you don't have enough iteration. I would like to try something actually. I would like to use a small number of neuron here to see how the performance looks like. And so the error here is 5,297. Let's see what's going to happen in this case. Is the network will be able to grasp the performance? Because sometimes when you have large number of neurons, it might, you see, so it gets worse, right? But not very bad actually, not very bad. So with a less number of neurons, still you can get a good performance or acceptable performance. Let me try 15 and 5. So in the first hidden layer, and then the second. Of course, this system, this neural network has one output. So it's 6,000. This is the error. Still, we have some conversion. Of course, the accuracy of the model depends on the type of application that you have. I would like also to show you something that might be interesting is we can draw the relationship between the actual and estimated response at both cases, like the training and testing case. So maybe when we see the characteristics, that will help us to see if the model is good or bad. Okay, let me go down here and then add a new code. So what I want to draw now is the the actual and the estimated response at both training and testing cases. Let me just do it on training first and then testing. So what I can do is I can say I would like to, of course, if I'm gonna draw the x-axis, I need to know the length of the y, like because when we took 80% of the data, so this means that it's the number of records time 80% for training and the number of indices which is 20% for testing. So I will call this indices, okay, and I'm gonna define indices equal. I don't really. I should not maybe define it as indices. Let me call it t, for example. Like t is the number of samples, and I'm gonna call it range to know the length, and I'm gonna say length of y test. Okay, so this should actually give me the size. Let me call test, see what test has. So it has from 0 to 439. This is the elements in T. Okay, now the next step is I would like to plot the characteristics. So I would say plot, I'm sorry, BLT dot figure. Let me define the size of the figure, and then fig size equals I will make it a little bit larger now because I think the data set is huge or larger. So and then I would like to say plot uh, dot plot t comma y test, and I'm gonna, in order to add legend actually um, for this figure, I can add label, can define the label. In this case I'm gonna call it actual, because I always say actual and predicted response. And I can also include line style. This is some of the options um, of the drawing. If you like, add line style, okay, equals, and then I can make it like dash, and I can add marker equals, and I'll put O, for example. Okay, Now I want to draw on the same graph the y test predict, right? Y test predict, and I'm gonna call it predicted, okay? And I will change, I will keep the line style. I can make the line style like, I think dash dot could be, or dot maybe, and keep the marker at the head. And then I can say plot dot title. Then I'm gonna say actual and predicted values or response, if you like. And then I'm gonna add, if you would like to add the X label and Y label, that's fine. And then you can say plot legend. Okay, that will be the legend. And then I'm gonna add plot dot grid true. And then after that I will say plot dot show, like this. Let's see how the plot will look like. I think we have a problem with the dot, yes. So let me just make it here dash as the previous one. True is not, oh, also true should be capital, okay, to add the grid. Here we go. So this shows the orange one is the predicted response, and the blue one is the actual response. Of course, as you can see, this, because of the range is small. I mean, it is small, but the variations are really too much. So that's why maybe we should like change a little bit the dimension, or if, for example, let me make this, for example, like maybe 15 or 16, 15. Yes, and make this, instead of, I can make it 4. Here we go. So that shows maybe a little bit better the difference. Of course, you can plot also the error, if you like, the error difference between the actual and estimated response. So for example, if I would like to draw the error, maybe I can just add a little piece of code here, and if possible I can just draw y minus, I hope this will work, control C, control V. So I subtracted the y test minus, yeah, I can do it here, minus y test to predict, and I would like to draw it. So here I'm drawing it. All right, it says no legend. I think we don't need a legend here. Okay, here we go. So this is the error difference between the actual and estimated response in the testing case, right? And if you would like to do that in the training case, you can just add a new code here for, and call this actual vector response in training case, and then this should be train, and this should be train, right? And this should be train also, to get the actual size or correct size. Here we go. So with, of course, this is a longer record. It's 1750, which represents 80% of the data. If you like, you can maybe move this up, so you have the case of training first, then the testing second, right? And this is the error. Let me just run everything one more time to make sure that the program is working fine, so you can utilize it for any other application. This is basically can be used for applications such as maybe stock index prediction, maybe uh, like as we do here, river flow prediction. So I think we should write this. This is in training case, and this should be in testing case. Of course, if you are writing like a research article, you might want to include some of these figures. Of course, you need to save the figures and make it. Of course, this error is calculated over testing. I mean, if you need to do it over training, I don't think we need it in a paper. I mean, maybe you should increase the number of criterias that you are utilizing to calculate the error here, like the mean square error, the root mean square error, the standard deviation of error, or the VAF, or and many other criteria you can utilize in this case. All right, I hope this clarify the use of a neural network, a simple neural network, and yeah. All right, so this concludes the session of neural network. Thank you.